Teresa, it's your chance to correct me today. Good morning.
Good afternoon.
Thank you for joining us today. Dean's lecture. Our speaker today is one of the most prolific researchers and innovators in the field of engineering. Garry Feather's research lies in microelectromechanical systems, and in this area he has contributed to over 250 research publications. I repeat that, 250. And he holds 13 patents. Garry has bachelor's and master's degrees from MIT, PhD from University of California in Berkeley, joined Carnegie Mellon in 1994, and he was named director of the Institute for Complex Engineering Systems in 2006. In 2013, he became Associate Dean for Research in the College of Engineering, appointed by yesterday's speaker, Jim. And last July, Garry was appointed Vice Provost for Research for Carnegie Mellon University. He holds the Howard M. Wilcoff Professorship of Electrical and Computer Engineering. He is also faculty member in Robotics Institute and Courtesy Professor in Mechanical Engineering and Biomedical Engineering. He has served as a technical co-lead in the U.S. Advanced Manufacturing Partnership, where he worked with industry, academia, and government to launch what's known as the National Network for Manufacturing Innovation, NNM1. He then co-led the proposal that landed the $70 million pilot institute for NNM1 called America Makes, and he currently serves on its executive committee. It is my pleasure to introduce you this distinguished scientist, educator, and innovator, Dr. Garry Feather.
Thank you, Dean Babers. I appreciate the kind words and introduction. That's my dog, who is enjoying a ride in the convertible. I'm going to talk today about manufacturing innovation, meaning how we are working with industry and government and, of course, with the universities in order to accelerate the adoption of new techniques in manufacturing. And, of course, there's a lot of motivation in the U.S. for this, but it's actually true across the world. Manufacturing is one of our strategic research areas in the university as a whole. I'm not going to go through this list, but you can see we have a number of key areas. A lot of these overlap with interests here in Qatar at Carnegie Mellon, and actually just interests in Qatar as a nation, quite honestly. You heard about smart cities yesterday from Jim. I'm going to focus on manufacturing today. Why do we care about manufacturing? Well, of course, this is a U.S.-centric slide, but it shows the gross domestic product broken up in services and durable goods. And if you look, as I think most of you probably know, services in the U.S. Dominate the economy, but manufacturing is still about between a quarter and a third of what the services are. And then if you look at the actual manufacturing that I'm really talking about in terms of durable goods, we've got a little bit of an uptick in the last few years. It's fairly flat, but what's heartening is it's not going down. The dotted line is non-durable goods. That's things like mining and forestry and so on, and that may be going down a little bit. So if we look at U.S. trade in goods and services, this is really where the country, where U.S. is looking at how to reshore manufacturing. There's a large trade gap, of course, with importing of goods, and this is where, and you can see it's been widening. This is where there's an intense effort to try to narrow that gap. What's interesting is, of course, both imports and exports of services is much less, as you might imagine. This is another reason why getting more exports of goods is a good thing. It drives economy of scale with larger scale. But we do export more services than we import by a tiny bit. So it's important for us. It's critical for the economic growth. It's actually, we think manufacturing is critical for the economic growth of any country. But certainly for the U.S., that's the case. It's a significant part of the domestic product. But more, and it really drives a lot of what we call good jobs, jobs that are at the top of the pyramid and create a lot of service jobs under them. And that's one of the critical points. The other reason we're interested in making sure that manufacturing is robust in the country is its intertwinement with innovation. And this is something that I think our country, in the U.S. at least, was kind of lost on people for about a decade, at least maybe 2 decades, of being asleep at the wheel, thinking that we could simply be a service economy and survive in the long term. But it really drives home, if you look at this cycle, in terms of what's done mainly in universities and research institutes of basic discoveries, inventions, aha moments. These are made into prototypes. And it's when you get into this cycle of, which is more in line with commercialization and manufacturing of pilot production and scale up, that drives then process innovation, which drives the manufacture of new products because, of course, then those new products are available for researchers, whether they be things like characterization equipment, new manufacturing processes, because of equipment that is now available, and that drives then new basic research. And I think it's this linkage going full circle is sometimes lost on people, and this is what's critical, and I think this is one of the critical reasons why I think this is true in any country. You really should be focused on how to keep a core manufacturing expertise within the country. So it's hard to do. One of the biggest problems is, and this is true of any startup, any small company, but also in large companies that want to adopt new technology, they have to bridge these valleys of death. It turns out there's 2 of them. You've probably heard of the valley of death for small businesses. There's a valley of death in terms of technology innovation that's going from applied research or a prototype, and then how do you scale that into production? How do you make? But then there's this second gap, which is really the scaling part of it. You might be able to manufacture a handful of products. Maybe you can even manufacture them in your garage for 100 a month. But if you wanted to build 1 million, how would you do that? That requires a different level of innovation. It also requires at least 1 to 2 orders of magnitude of cash. So that solving the second valley of death is incredibly expensive, and that's why it requires partnering. This is not something that is generally can be done alone. So back in 2011, President Obama announced this group called the Advanced Manufacturing Partnership, or AMP. We called it AMP. We were proud that he chose Pittsburgh and he chose Carnegie Mellon to make the announcement at our National Robotics Engineering Center. It's in Lawrenceville on the shores of the Allegheny River. And you can see some of the robotic equipment in the back. He's in the high bay giving this presentation, this speech. And he announced that he's forming this group. It was going to be a partnership with 5 universities, 13 companies, and then a bunch of government agencies to get together, effectively lock us in rooms for several months, and then come up with actionable items of how do we move forward on this idea of reshoring manufacturing. So I was in a room with the Dean of Engineering at the time, the one that preceded Jim Garrett, along with the president of the university, and actually the provost, I'm sorry, came in to my office. And so I knew something was wrong at that point when I've got them in my office instead of me in their office. And Gary, we have this new thing called this Advanced Manufacturing Partnership. We've been asked at Carnegie Mellon, who do you think would be the right person to help with this thing? And I go, I'm not sure. Maybe. I started naming other professors, and they go, no, Gary, we think it should be you. So I was drafted and spent the next 8 months shuttling to Washington, locked in rooms with people who do policy. And of course, I'm not a policy expert, although I've become a little bit of one, I guess. But they convinced me that I was one of the most important people in the room because they had no idea what the technology was, and we needed to work together. And that's another area where partnering matters, is when you're developing policy with the government. If they're locked in a room by themselves, it can get quite scary, actually. So we went through this process. It came up with an actionable item, and one of them was to create a series of manufacturing innovation institutes that extended this idea of partnering into tangible action. We create institutes that kind of a hybrid of something like the Fraunhofer Institutes in Germany, where universities, the government agencies, small businesses, large businesses, community colleges, national labs would all have a place basically to convene, to share ideas, share intellectual property, and move forward. Sounds easy, right? So it turns out, if you fast forward, there's been 8 of these institutes formed now. The first was called America Makes, and as Dean Babers was mentioning, Carnegie Mellon, starting with myself, had pushed forward to create a proposal for this. It's not run by Carnegie Mellon, it's run by a nonprofit that is focused on additive manufacturing or 3D printing. After that, a series of other institutes, you can see the timeline down here, have been formed. The latest was just 2 weeks ago, the Advanced Functional Fabrics for America Institute, which is led by MIT, it's in Cambridge, was announced. And there's another couple, there's various opportunities from the Department of Energy and from the National Institute for Standards and Technology of new institutes that are coming down the road. So there's 8, and there's going to be up to 11, I think, before President Obama leaves office. And you can read the title. A lot of these have to do with materials-related institutes with photonics, smart energy, power semiconductors. So Carnegie Mellon, of course, has always been a partner of this sort as well, right? So we feel that we fit very well in this kind of ecosystem working with these groups, and we do this at the Pittsburgh region. We also do this worldwide. So we're very proud of that. If we look at what are we doing at Carnegie Mellon in advanced manufacturing, we have a very focused group at Carnegie Mellon. We can't do everything. We're a medium-sized university, if you will, of about 13,000 students in Pittsburgh, and then you add a few more worldwide. So we pick and choose, but we're doing work in energy technologies. This is water-based battery work that Jay Whitaker, a professor in chemical engineering, does. He's spun off a company, a successful company called Aquion Energy that builds these batteries in the region. We're doing work in additive manufacturing, work in bioprinting, robotics, and we have quite a bit of expertise in chemistry. We have what we think is going to be a future Nobel Prize winner in Christoph Mattagesti, who has invented this thing called atom transfer radical polymerization. It's basically the basis for all modern polymer technology to build polymers at a controlled length, which before that invention was not possible. And so a lot of new polymers get invented in the Pittsburgh region. So, you know, I'm only going to have 3 slides on my personal area. I'm going to focus mainly on additive manufacturing robotics, but I felt if I'm giving the talk, I should at least tell you a little bit about what I do. So I got 3 slides on that. I work personally, I have a number of grad students. I work in the micro-nano systems area, or micro-electromechanical systems, but there's a lot of faculty that do that. I work primarily on integration of CMOS, which is an electronics commercial technology, and I'm doing a lot of work now on soft type of microsystems, especially soft neural probes and other wearable electronics. One of the, and this tells you my interests right here in resonance systems. I do a lot of work in gyroscopes and so on. A lot of this is all silicon micromechanics. So this is fabricated in a large nanofab facility. I'm interested in stretchable electronics, neural probes, 3D printing. This is some of our most recent work looking at making effectively silicone rubber as patches to put on your skin like a Band-Aid, and it conforms to your skin. And the key is then being able to embed electronics in that material along so that you now have a mechanism that can intimately interact with your skin, for example, to read out biomolecular signals. This requires then having the right electronics, wireless, and so on. What way we're doing this is using conventional electronics, but trying to get it into the elastic material without it breaking. So it turns out that's quite a challenge. We've made a breakthrough recently where by putting gradients of stiffness in the elastic material and making it a little stiffer around the chip, instead of it delaminating, like this is when you pull it, the material rips apart. Here, this is under large stress, and it stays together. So we're working on these kind of, again, fundamental research. This isn't a product yet, but this is the kind of basis with, and patent that then creates then new products down the road that people will buy on amazing, systems that you'd stick on your body, for example. So we're investing at Carnegie Mellon. We've got a new engineering building called Scott Hall. It's going to house biomedical engineering, our Energy Institute, and also the institute I used to lead, the Institute for Complex Engineered Systems, which is basically think of it as our research accelerator for engineering. In addition, it houses a new nanofab facility. This is a large 11,000 square foot clean room that is being the new home for our various equipment for doing these kinds of processes. So we're hoping this is also a way to bring more industry in. So we talked about America Makes, and this is the institute that kind of drives 3D printing, or what we call additive manufacturing. And 3D printing is usually used as a prototype, a term for the rapid prototyping if you have a MakerBot or one of these inexpensive types of machines. Additive manufacturing, a lot of it is very serious type of manufacturing for things like jet engines, and done with materials like titanium. So gives you some idea of the things you can make are three-dimensional objects. This is in titanium, so this is incredibly tough. You can't bend that, for example. So a lot of work has to do with these kind of lattice-type structures. There's a lot of different ways to do additive manufacturing. The primary focus that we have at Carnegie Mellon has been on something called the powder bed fusion. This is a powder of metal materials, and then either laser or electron beam is shot as a beam at the material to locally melt it and build up structures. We also have a lot of work on extrusion, which is, think of it as a hot glue gun on a CNC machine, if you will. So extruding polymer locally and building that up layer by layer to create structures. So there's a lot of interesting research on this. It turns out you can make a lot of different types of parts. People do additive all the way from building buildings. Okay, so there's additive manufacturing of taking concrete and extruding it out of a tube and digitally manufacturing a building. And this is actually happening. And bridges now are also being looked at in metal bridges this way. All the way down at the nanoscale, we have an interesting machine called a nanoscribe machine that can do 3D printing down at sub-micron scales. And obviously, most of the interesting commercial work is in between. It's this metals and polymers type of work. And there's a lot of hype. There's a lot of promise to this technology. If you've read any of the literature in the just regular kind of layman's literature about this, about basically push a button and out comes the part. Okay, you can scan and create a digital model and you get this perfect part out. It's on demand. You can customize. I could change the part a little bit because it's all done on the computer and print out a new part. There's a lot of complexity. I could make lattice structures. I can do internal structures inside of a part that you couldn't do with machining technology, or you'd have to assemble. So this would be less expensive, put functions in it. But what a lot of people are excited about is, in principle, this is all digital. You push a button. You don't need a lot of skill. Okay, I don't have to know the tricks of how do I CNC machine or weld or things like this. So it becomes democratized manufacturing, distributed. A lot of people are excited but also nervous about what that means in terms of disruption of supply chains. So I'll go through these slides because this is somewhat redundant with what I just said, but just to drive home the point about these promises, the idea of direct digital is this ability to be able to make the part on demand. There's less inventory. A lot of people are interested in this if you're out in a remote site. And for example, our plane, we needed a part for our plane when we departed from Philadelphia, came here, and they had to go find the part. Well, if it wasn't in inventory, what would they have done? If they could have had a machine and just say, well, I'll just download the digital file, push a button, and make the part, right? So you can, the promise is you can do that with this technology. You can develop these internal assemblies. These are various type battery housings, injection mold parts. These have very intricate internal structures to them. They'd be expensive to fabricate in a conventional way. Here, it kind of comes for free. You can do a part like this as inexpensively as a part that's kind of just a solid chunk of material. And then you can integrate part. There's been a lot of stories of manufacturers taking an assembled system that might have tens of parts that were assembled. For example, the centrifuge that was made by a manufacturer in Germany, that would have 32 parts. That can be made with one part. Okay, and so that creates efficiencies. General Electric, one of the famous additive parts is the injection nozzle for their jet engines. That used to be 35 parts assembled together in metals and expensive technologies. They've changed that into just a single part that's created to replace it, and it's a much better system now. It both functions better, it's also cheaper, so they're very happy. And then there's this design aspect, okay, which has, it's just a different way of orthogonal thing about customizing, being able to democratize the manufacturing so that an artist, a designer, can partner more easily to create the type of products that the consumer may want and right now are unable to get because everything is batch manufactured as opposed to customized. This is an example of a fairing on an amputee, and they get to pop on different fairings depending on, are they going out to the opera? And actually, she's proud to show people her amputated leg because it's so cool. People are just excited. And it's kind of weird, right? It's like, they're excited to see what is she wearing. It becomes kind of like wearing a jewelry. And then if you're out on sports, maybe you wear some other type of device. So we have one of our researchers, Steve Collins, works with this type of additive manufacturing to make the parts for his exoskeletons. These have to, as you can imagine, be very tough. So again, using additive manufacturing to make custom exoskeletons for a specific human now becomes possible, and done in titanium so they hold together and are lightweight. There's a lot of underlying research. Jack Buth is a professor in mechanical engineering. He's kind of our lead on additive manufacturing. He works down at this level of studying the process of how do you melt the metal, and then how does that relate to the microstructure. Okay, so that's really important, because it turns out this idea of pressing to print doesn't actually work. You press, you get out your part. Part isn't quite the right geometry. It's not as strong as it should be. There isn't trust that the part actually works the way it's supposed to. And that's really right now the main thing holding up the industry, is having that trust that the part that people claim is made, that's spec'd, actually comes out that way. This is especially important for aerospace or a safety critical application. The part's got to work, right? And that's what Jack's working on. He works with Tony Rowlett, who's a professor in our material science and engineering department, on then the deep microstructure of these types of devices. They also work with Fred Higgs. Fred Higgs is a professor in mechanical engineering. He's a tribologist. He's looking at, again, these metal structures are made from a powder bed of titanium, again, shot with a laser or an E-beam writing, and how the powder is handled and spread is a critical part of getting a good part out of the system. You can imagine if you had a void in the powder bed, you're going to have a void in the part, and then that could compromise its integrity. So he's a critical part of the team. And we've been developing this all in a facility that's relatively new. We're one of 4 universities in the United States that have both the electron beam machines and the laser powder bed machines, so that we can compare processes. And we're building up more capacity with various types of characterization. This is the team. I apologize, there's some extra writing on this, but we go all the way from looking at powders all the way to the microstructure of the materials. There's a whole group of faculty that are partnering together to work on that technology. So another area in additive that we're excited about is bioprinting, which is more futuristic, of course, but I think the future is coming fast in this area. Adam Feinberg is a young faculty in biomedical engineering. He's actually moving in our new Scott Hall building. And he, along with his graduate student, T.J. Hinton, have invented this idea of how do you make a biostructure with 3D printing where you're layering goo. Okay, you're layering things like alginate and collagen, which don't hold together, but once a device is made, the structure will hold it together. Okay, and so what's happened in the past is that devices have been written, and it's kind of like this Salvador Dali picture. They just don't hold together, and it doesn't really work. What they've done is used a hydrogel matrix and a low-cost printer to print the biomaterial. This has got ink in it, so you can see it, into the hydrogel like a swimming pool, and the hydrogel holds the part together while it's being printed. Once it's all done, it can be released. The hydrogel melts at higher temperature. You just raise it a little bit in temperature. It's like a swimming pool, and you pop the part out. Okay, incredibly simple, but something no one's done before, and it's a breakthrough. So now people are starting to print really complicated things like this artery that was scanned. This is a human arterial tree on the site of the heart, for which is an issue if you've got a coronary issues with your heart. they have done an MRI scan to get the exact shape of the arterial tree, and then print a faithful copy that is directly implantable, okay, in collagen into the body, and then shown that in fact, and I think I can't use my clicker for this one, that in fact it can be infused. You can see the ink coming in through the tree, and this has never been done before. Okay, this is all 3D printing direct, again, print from the scan, so you can see the power of the customization. So in a few years, there will be implantables that people will just print out for your personalized body parts that you might need. This is an example not for an implant, although maybe someday it will be, of taking the human heart, scanning it with a 3D tomographic scan, and then making an exact replica in the biomaterial scaffolding. And this is done not to implant. This is done to study the structure and the biological nature of the heart. So they're looking at this for various types of research. Another, I don't have that picture. Oh, okay, well, so I also had one it's come, I'll skip it, I had it out of order. So another one is this rat brain, a little creepy, but that's also a scanned brain. It's full structure, and that's done in order to understand the structure. So this also becomes a fascinating teaching tool for teaching the kids about biology, and it's kind of really hands-on. In this case, of course, you don't have to kill a rat anymore either to study a lot of this stuff. So here you just keep printing these brains out and having students look at them. And in fact, these could be dissected. Let me go back a slide. I wanted to shout out also to one other faculty, Erica Fuchs, who's in our engineering and public policy. So we're doing manufacturing all the way from the science and a lot of the applied work all the way to interacting with the government and looking at policy. Erica's kind of at the tip of the spear on that. She's been focused on deeply understanding the modeling of supply chains, the modeling of cost structure for these advanced technologies like additive, but also other robotics technologies, electronics technologies, and understanding where's the right place to make these things. Is it actually the right place to make them in China, in South Africa, in Qatar, or in the U.S.? And this is partly to not, to understand this ahead of time so we don't buck a trend that's going to be obvious from a business sense. Let's instead then look at, for example, in the U.S., what are the products that should be made in the U.S.? Okay, let's focus on those and not on the ones that should be made in Qatar, right? And vice versa. And so that requires a lot of deep modeling and thinking about what's the right business thing to do. And this is not in a vacuum. She then works with other faculty on these topics. Okay, the last part of my talk is the fun part. It's on robotics, which is, so I have a lot of gratuitous videos of robots that are going to be making things. So this is one of the robots that was made actually for competition. This isn't actually for manufacturing, but for things like hazardous waste cleanup and emergencies and so on. It's part of a competition. This was called Chimp and made by our National Robotics Engineering Center. So if you look at what we've done in robotics, the underlying in robotics is autonomy. It's understanding how to fuse sensors together, extract knowledge from that, and then be able to do path planning and understand how to use actuation appropriately. There's been a lot of work on human-robot interaction. How do you get humans and robots to cooperate? That's really important for the future of manufacturing, for assembly. There's been a lot of work on, this is from Howie Chozet, on both hexapods and also on snake robots in ways to make modular robots that can go in places that regular robots can't, but also make robots really quick. And I'll talk more about that. We're doing a lot of work on assistive technology, and then there's just work on control, things like ball bots that you might see in a department store to help you find the cereal in the cereal aisle, right? But you know, when you look at manufacturing, this is the reality of robots in manufacturing. The robots are in cages because there's a lack of trust. The robots don't work with humans. People are worried they're going to kill the human or hurt the human, so let's put it in a cage. Although one would argue that it's the robots around here, it's actually the human that's in the cage to keep away from the robot. So how do we work around this? I mean, what's the future look like? The themes that we're focused on are CAD to code. How do you make modular robots, make them fast, you know, and simplify the making of robots? Turns out it's incredibly expensive. That's where a lot of the non-recoverable engineering expenses come from. How do you get to this mass production in quantities of one, so we can get the advantages of mass production, but be able to customize? Humans working with robots safely, doing multi-scale manufacturing down to low levels, and then, of course, this idea of how do we exploit big data in this kind of environment. I'm going to touch on the top three in the interest of time today. The first is this modular robotics idea. So Howie Chosette, the professor in Robotics Institute, has been working for years making snake robotics and other multi-robot systems, and he's come up with this way of making snap-together joints. Now the thing is, what you might not realize is he's patented the technology to create these, and the real key thing is no one had ever patented the idea of using Ethernet to connect robots together. It's like, well, duh. Well, it turns out that makes a big difference, right? That's really a key to this modularity, and a key to the modularity of the software. So if you look at, there's a little noise to this, but this is a graduate student building a robot from these modular components. In this case, it's an arm, and he's going to do it in about 20 minutes. This is after, we were joking, after he had a 5-hour energy drink. But the point of this is going to work. Okay, so here's someone putting a robot together, and then it's going to be programmed as well. Okay, and then custom programmed. So in this case, he's using gesture-based programming in order to do the position control. This is hard. Okay, I mean, in order to get to this point in terms of the research, once it's done, though, this is really democratizing the use of robotics. The amount of engineering effort that normally a person has to create a new robot and be able to deploy it in the field takes over a year, and it costs about 3 to 4 times the cost of the robot. So the robot is cheap. It's trying to get it to be used in the field is the hard part. So if we look at then, so that's a base technology. If we look at this idea of mass manufacturing in quantities of one, that's really been focused on how do you make, I mean, in the case of Robotics Institute, they've been looking at how do you make big things like ships, like airplanes. These things are done right now with something called monuments. They're linked together, very static, very expensive, not custom technology. The vision is to be able to create a more flexible environment that can build these types of products with robotics helping humans in a cooperative environment. So that's being done with, in our case, both, of course, under the hood, lots of research, but then demonstrating the capabilities with various types of robotic components that work together. And this just gives kind of a vision of the idea of having robots that are working, that are mobile platforms holding on to wings and wing spars that normally monuments would be fixated. So this becomes a very flexible manufacturing environment. One of the keys is how do you program these things then to be accurate? So you have these large-scale objects, and then you still have to get a bolt in a hole. Okay? Getting a bolt in a hole is one of the hardest things for a robot to do. Well, our researchers have been very successful at building out this technology.
But the human can push
and
and pull,
here's a demo with some of the visitors at our high bay
and then the
in
robots
Pittsburgh.
do all the work.
And this just simply
to
shows, for example, the
wherever you want it to
simplicity
go.
of creating mobile robots
Spin the
that
skin,
cooperate and
move it
can
in
cooperate
place,
with a
and maybe
human.
steer it around.
It seems really
And you can do
simple,
this
but
for
how do you get robots to
however many
hold onto
robots
an
you want
object
or
and then
whatever large
the
object
human
you want.
wants to move it away?
Go ahead,
They're
yeah.
working together. So the robots are communicating with each other, making sure that the loads are balanced and accurate. And so this is then extended into how do you, we have videos, they're putting the spars in the wings and things like that as well.
Key to custom manufacturing is rapid
The
setup.
other, well, let
The time
David
is all
talk.
spent setting up the manufacturing process. 98% of the time is spent setting up.
So David Bourne is another faculty in robotics, and he works on how do you work, robots do what they do well, humans do what they do well, they work together. It turns out robots are really good at precision, okay, and they're good at understanding directions. They remember things. So I look at this as, this is a graduate student who's building a Humvee frame, welding it. So the graduate student was just trained at welding, for maybe a couple months. He's a novice welder. He teams with the robot. The robot actually speeds up things by telling him, it's kind of like opening an IKEA box and trying to build your furniture, right? He's like, the robot tells him, well, what parts to put together where, and then it checks and goes, oh, you did that wrong, and to move it over a little bit. That saves a huge amount of time. Then the robot can weld certain things. If it's really awkward, the human welds, in this case a student, will weld other parts. So this particular, so it's all about, it's not about what you automate, it's what you do fast and well, okay? This particular work was part of a competition sponsored by the Defense Advanced Research Projects Agency called IFAB, where they pitted 3 professional welders, assemblers, against this graduate student and the robot to build these Humvee frames. It turned out the graduate student and the robot did it in 1/10 the time of the professional welders. Okay, maybe some of that's because they're union workers, I don't know. But still, it's amazing. And it turns out that goes direct into the bottom line, okay, in terms of the cost. So exciting technology, it's where that's headed. So I'm at the end here, I just want to say, well, where are we headed? Well, obviously it's doing this kind of work. We're kind of looking at this, choosing where we're focused in manufacturing. It's in technologies like additive manufacturing, like robotics, but we also span areas from design to policy with these manufacturing technologies in between. And we're looking at creating programs where we can accelerate the innovation of the science into products. So that's one place right now we're starting to pull our machine learning people in and see how can we better accelerate, how can we make apps for that effectively. So that's an exciting thing coming down the road. You've seen the robotics work. I think a big part of this is human-robot interaction. That's how we're going to sell this in the US, because obviously everyone's worried about robots. They're going to take all the jobs away. It's like, why should we work on robots? We should destroy robots. And it's when you start to have robots working with humans, that's what's creating the jobs. It's enabling the humans to do things, and together they can do things that neither one could do by themselves. I talked about machine learning. I mean, the autonomy aspects of this are huge. And then we haven't talked about cybersecurity, but we live in a world where we start to automate, and especially it's scary when you start doing action, right? Are you worried? I'm sure everyone's worried about internet attack, about their passwords and things like this, and their information on the computers. But imagine you've got the same problem, when you're dealing with both infrastructure systems like you heard about yesterday, but also robotic systems that are acting, those can be hacked, and then, then you have other serious consequences. So we have to be able to protect that kind of infrastructure. And with that, I just want to thank you for your time, and I hope I didn't keep you too late from getting some food, but if there's time, I'd be happy to take questions.
Thank you. Fascinating. Well, I need to ask the first question.
Uh-oh.
When you were showing the heart and the veins, you brought it home to me. This 3D printing or additive manufacturing, if you print a tennis ball, is this a rigid object or can you screw it?
It depends on the material. That's the beautiful thing
You
about,
are able to screw it.
yes, with certain types of 3D
So the
printing.
arteries would be contracting.
Oh, in this case, yeah, for the bio, this is made out of collagen, so these are direct materials that your body already incorporates. Yeah,
They
absolutely.
gave me 10 years after the surgery, maybe I have a few more years.
They can, well, we need to scan your heart right away.
Questions, please, yes.
Yes.
Thank you so much. You mentioned light material interaction and as one of possibilities for manufacturing, and I just would like to mention that there might be a really good chance for a collaboration between various campuses here, like, putting it in practice and maybe submitting a joint, say, an exceptional proposal to QNRF. Like, because usually when people come to studies to these problems, the level of technology usually requires deep understanding of the fundamental science. That's what my group is doing, my students doing.
Mm-hmm.
And, cooperating with people from computer science and from biology, that might be a really good case for submitting an exceptional proposal to QNRF. And then it would be a kind of realistic implementation of the ideas and an opportunity to build things which would be involving fundamental science, light material interaction, which might be of potential interest to QNRF, who are looking for personalized medicine that Dean Weber just mentioned. And, it might be a good case to go forward.
Well, let's follow up afterward. I'm happy to make the connections. Usually, as you know, with any collaborative work, it's really about making sure that people want to work together.
Definitely.
Then I guess it's my job as Vice Provost for Research to try to make sure that, that we don't have too many problems with rules kind of restricting us to what we can do together and how do we get the money to do it. But yeah, I think that's
But light
a great
material,
idea.
and just for you to keep in mind, light material interaction and material breakup, such as the liquid jade breakup, actually it's my current projects, which are running here. So with the students both in Carnegie Mellon in Pittsburgh and students here in CMUQ.
Mm-hmm. Excellent.
You started off pointing to the trade gap, and at some point during your talk I got the impression that at least in some areas it would be very easy to move productive capacity to just about anywhere in the world. Why not make it in Singapore or Panama? Or
Yeah. Or Mexico in the case of the U.S. in most cases, yeah.
So is that bad news for the...
It is bad news. I think that's why they're...
let's say to an environment where tax policy is more favorable or more certain or something.
I think it's certainly true that the recommendation for a set of a national network of manufacturing innovation isn't in isolation going to help by itself. And in fact, the Advanced Manufacturing Partnership, they had two waves of this, 1.0 and 2.0. They've created a set of recommendations that also include policy on trade, on regulatory policy, trying to provide incentives to keep advanced manufacturing in the U.S. Without being isolationist, right? So it's kind of a trade-off there. And some of them, of course, the companies that have been on AMP definitely were all in on idea of having more friendly tax policies in order to make sure that there's incentives. So this is again where there has to be a partnership in terms of the system working together in order to affect change. You can do all of this great research, but if we have policies that just drive businesses when they scale up to go out of the country, it's actually not going to help. So we're trying to, so on the research side, we're trying to do what we can. I think this is where, both in business, but also like in our engineering and public policy, where they can help to try to inch the needle by educating Congress, our legislators, and the folks in the White House about what we think they should do. And so we do that to the extent that we can be an agent for change. I think there's a question behind the camera.
The 3D printing, the potential for it, the positive potential for it is amazing. And I'm worried a little bit about the regulation. Like, if anyone can print any part anywhere, how does that infringe on the patent for that part? Like, how does that affect the, why would anyone start inventing anything if anyone can print it for, much cheaper anywhere they want?
It's a great question, and I think it's the same question probably that the music industry had faced when the music was digitized, right? So any industry that gets digitized ends up having this type of disruption, and then they find a solution. Now, it might take years, and it is true that the regulatory agencies in the governments tend to be the last to actually come up with solutions. I think this is another area where universities can help work to provide the type of information to the government to provide incentive that the regulatory agencies can stay on top of things. For example, we're in the midst of trying to push through a bill with our Congress friends that will allow the Federal Aviation Administration to start a research program, an early research program on certification of additive manufactured parts, so that they can be in front of the wave instead of being reactive and lagging. So because they see, especially in aerospace, a series of requests for certifying parts that are going to be flying in planes that we're going to be inside of, and so there's an obvious concern. Unless it's like a bracket for your seat, but if this thing's going in an engine or a wing, it better work, right? So this is serious stuff. So, but there's got to be regulatory policy that's driven by technical common sense and not by kind of guessing, and also hopefully not sped up for having access to that information. And medical is going to be the same way. I'll let you moderate.
I guess this is more a comment rather than a question. So when you were showing the video on the robotics, human collaboration and manufacturing with the 10 times speed, the thing that came to my mind, all the news from Tesla last week about the problem they had this quarter delivering demand, and then the pre-orders of the 300,000 cars, where the biggest problem was how fast can they deliver these cars. So I guess when you put that in the context of sort of innovation of new products, this could be a huge advantage for
Absolutely.
the US.
How do you create, especially for both Tesla, also this company Local Motors that's trying to use additive to create cars. This idea that Tesla wants to create more customization, right, and on-demand construction, and I think these types of technologies are going to be game changers for them to lower the cost of the product and be able to scale up. So that the job, and again, I think this is part of this is so the jobs don't just go to Mexico. The idea of going to Mexico, and in the case of a car, that's where it would be, because you don't want to ship the cars back overseas, right? That's why it would be Mexico. But that's all driven by effectively having a sledgehammer to pound a nail is kind of the solution, right? Let's just take low cost as we can, tax incentives, and it's still a crummy solution, but it's so cheap that we can waste. See, the solution should be, can we do this far more efficiently, and then it can be done, and then it can be done in the U.S. And be more effective. Of course, the argument has to be made, can you then have that conversion of tax policy, of other incentives to make sure that there aren't other reasons it would go offshore. But the same true here in this country. You'd want to be able to manufacture things here in the country, both so you have that virtuous innovation cycle, but also just things to be cheaper and more efficient, so you don't have to ship, especially large things you want to manufacture. You don't want to have to ship them here. How do you make them here?
One more question. Valentin.
Thank you. Very, very, very exciting lecture. The question is, how it relates to our campus, Qatar campus, manufacturing. I think that Qatar Foundation and Qatar is very interested in manufacture. And they have that vision 2030 that they knowledge-based. What's your vision? Our part, CMU part in that manufacturing. Which areas we can focus, robotics or something? What do you think on our relations with here in Qatar?
Oh, here in Qatar, how would that? I'm not sure I'm smart enough to figure that out, but I think, well, if we look right now at the resources here you're talking about in Qatar directly, or CMU?
CMU and Qatar Foundation.
And Qatar Foundation. So it seems for CMU, given the expertise here in computer science and business administration and information systems and biological sciences, that one would look at the overlaps in those areas, right? So I think from the standpoint, it's primarily going to be probably the additive. The 3D bioprinting is certainly an area. I mean, there was some discussion of how to tie that in, and possibly materials, some innovation with new materials. I could see is something that kind of crosses boundaries. Again, these are. So I'd have to say it's really going to be dependent on the local. It's really a grassroots thing, it's local expertise, and what do people get excited about collaborating on. From a business point of view, I think it to some extent it's opportunistic, right? It's like what is, I think there's an entrepreneurial play here that is going to evolve, and so that the university could play a role there, certainly the Qatar Foundation, to exploit that growth in the business. So I think those are the primary areas. I think computer science, I don't know. I mean, we're interested in tying machine learning into this to be able to accelerate science to product design, and so I think if there are particular folks here that are focused in those kinds of areas in cognitive assistance, then there could be a play as well. The thing is, that area is so hot, there's so many other places for researchers to look. There has to be a zeal for manufacturing as opposed to the 20 other cool things you can do with machine learning.
Thank you, Garry.
Thank you.